or maybe I should email you and actually, ask.
Yeah. So the main thing is that we're looking for is, are your answers sort of logically consistent, right? And follow the proper physics, right? But for some of the questions, there's definitely multiple ways you can get to the correct answer. I think that's one of the challenges with this stuff and thermodynamics in general, right? Is you can look at it, all of the nucleation theory, as being a direct consequence of Gibbs-Thompson, right? You can look at Gibbs-Thompson as being a direct consequence of interfacial energy, right? And so depending on where you go, you can start. You can start from the interfacial energy, you can start from the Gibbs free energy, and you'll end up with steps that look very different, but in reality are just different ways of describing the same underlying physical phenomena, right? And that's not necessarily a bad thing. Right. I care about, if I give you a general situation, can you work out what's going to happen? Right. That's really the key thing. The key thing in my book. All right. So anyone have any sort of general questions before we get going?
Just actually, I have a quick question.
Yeah.
Will diffusion be on the exam?
Diffusion, no.
All right, let's get out of the exam mindset then and focus on the class. I've been talking about the exam too much.
So on Wednesday, for the initial part of our lecture on Wednesday, I'm going to actually just take a quick look at the exam with you guys. And but before we do that, I'm going to make sure that it is the first part of Wednesday's class will be just dedicated to you guys asking any questions you want, right? And of course, by that time, the exam will be completely written and ready to be posted. And you'll be free to ask any questions without worrying about, is it going to, affect what the questions are going to be. And then I will make sure that right after my office hours on Wednesday, the exam will be posted. But I'll give a few clarifying sort of remarks and statements on the in class on Wednesday, right? So I wanted to just hit one thing real fast, right? And basically, we talked about diffusion and a chemical potential gradient at the tail end of Friday, right? And before we talked about self-diffusion, we always just said that the composition is going to equilibrate, right? If we have a composition gradient, that given time, eventually the composition will become uniform everywhere. That's, of course, in the absence of any chemical potential gradient. And that in that case, there really the driving force, there isn't a driving force for net migration. It's just that the potential is uniform everywhere, and that regions where there is a large composition, you have more hops than a region that there is a low. And so eventually it equilibrates out, right? That effect is just simply due to the fact that the jumps are random forward and backwards, and you give enough time, and if each solute atom acts as a completely random walk, they're going to end up spaced uniformly, or not uniformly, but they're going to be uniformly randomly distributed. In a chemical potential gradient, we have a driving force, right? That the activation energy for a forward hop is less than the activation energy for a backwards hop. So in the forward direction, it's just delta G of migration. For the backwards, it's delta G of migration plus the chemical potential gradient, right? Right? So this bias is not particularly strong, but it's sufficient, right? If you remember everything from our Arrhenius rates and our Boltzmann statistics, we don't need a big change in energy to give us a very large change in rate, right? So this is a really important concept, right? And so the other is that the diffusivity in the presence of a chemical potential gradient is basically the same as our diffusivity without the chemical potential gradient, plus another exponential, or multiplied by an exponential term for the gradient, right? So what this basically says is that Fick's law and Fick's second law work just fine. We still have our diffusion length is going to be the square root of dt. Everything that we talked about before holds. It's just we have this extra term in our diffusivity, right? And that's just kind of the important concept that I wanted to get across. And this is explained very poorly in your reading. So I apologize about that. Okay, so today I want to talk about a bit of the added complication of now when we have interdiffusion, right? Diffusion and mixtures. So before we were talking about essentially self-diffusion. The homework 4 solutions are posted on Carmen. They should be right under the homework 4 assignment. They were posted there Friday. Or maybe Saturday. Maybe they went live Saturday. Right after class, I'll check. So for interdiffusion, we're talking about the case where we have, imagine either pure A and pure B, or a diffusion couple made of a B-rich material and an A-rich material. And by diffusion couple, we're just saying I take a slab of material B and material A, and I polish them so these are perfectly planar interfaces, and then I stick them together, right? They could be welded together. They could be just put in really close proximity with an external high pressure or something. The most well-known diffusion couple to you guys, even though you've probably never actually thought much about it, is actually a US nickel, right? Or any US coin, right? Where you have a nickel cladding on a copper core, right? So the nickel and the quarter and the dime. Actually, the nickel is just solid nickel. The quarters and dimes, right? Those are actually diffusion. Those are actually diffusion couples. And when I taught the physical metallurgy lab, the senior lab, we used to actually measure the interdiffusion between those. Those as part of our as part of the lab. But anyway, once we have a couple like this, and we have the interdiffusion of two different species, where the dilute limit doesn't hold anymore, things become a little bit more complex. And there's some theoretical wrinkles in here. And it also means that the analysis gets really complicated, right? So the quantitative analysis becomes really difficult. It's really sort of, I guess, maybe a good thing that I don't expect a lot of quantitative stuff, because as you'll see, you end up with a bunch of nasty nonlinear partial differential equations. And we could go through the motions and look at the solutions for a special couple cases, and go through the pain of trying to do it, but I don't think it actually enhances understanding much. So I really want to focus just on getting a really good sense of what the physical picture is. And the numerical issues, that's what computer software is for. But here, let's just consider a couple where I have A and B that form a full solid solution, right? They're completely mutually miscible. And I made a diffusion couple of material 2, which is rich in A, and material 1, which is rich in B, right? In general, the rate at which A moves through B is not going to be the same as which B moves through A, right? So what are going to be some consequences of this? Any speculation?
Speculation. I figure it's been long enough since I talked, answer one of these, so I'll talk. I think the consequences is that, well, it probably won't be a flat curve like that, will it? You have over there, won't the, if it's easier for A to move through B, won't the B del G be lower?
Well, so this is just gives you the this is the free energy of mixing, right?
Yes.
So we're this is a little bit idealized, right?
Mm-hmm.
So this curve is going to be a bit distorted, right? But we can still think of it in sort of the ideal case, right? So the point you're making essentially boils down to is that this curve being symmetric in the way that it is implies that it's that we're taking a regular solution model in which the AB bonds are pretty close to the AA and pretty close to the BB, right?
Yeah.
So why should there be a difference in the diffusion rates? That's a fair enough question, right? But let's just say that they are slightly different. I just wanted to point out that it is completely miscible, right?
Well, I remember back from the very first reading we did, actually, that having the ease of forming AA or BB bonds versus AB bonds is tied to the interfacial energy, not interfacial, the energy of the internal energy. It's been a while. And I remember if the internal energy is less than Okay, I don't remember I'd have to look in the book, but basically, if the bonds aren't even, they'll affect the internal energy of the system.
Yeah.
Like,
So in that case, we can assume that all that's sort of taken into account in our Gibbs free energy, right? So we have the system can lower, in this case, the Gibbs free energy, right? By making a solution that is uniform everywhere, 50% A, 50% B, right? Because of the entropy term, right? So that will still happen in this case, right? It's just something else is going to happen because we have a difference, right? If we think about this flux, if A moves through B faster than B moves through A, we're going to have a different flux, right? So what does that imply about our mass transport, right? Do I have more? I have more mass going this way than this way. So my interface needs to move. So the position of what I call my interface is going to change with time, right? It also means that my diffusivities are not constant. They're going to be composition dependent, right? Depending on the local neighborhood. A moves at a different rate through A than it moves through B. So I have to take that into account. So it's also, we also have another idea of what is our, if these make a solid solution like this, it implies that they have the same crystal structure. So that means they're occupying the same lattice site. So that means the mechanism here is essentially vacancy diffusion, right? And so if I have A going this way, what way do I have to have vacancies going? I have to have vacancies going the opposite to A, right? And the same thing, if I have B going this way, I have vacancies going this way. And if I have a mismatch in atoms, it means I also have a mismatch in vacancies. So I have a net amount of vacancies going from 1 to 2. Which is kind of an unusual situation, right? So let's look at the first part of this, right? So if we have this d tilde term that we'll define much more carefully later, we'll call this the interdiffusivity of A and B. And it's going to be concentration dependent. So that means Fick's second law, before we pulled the diffusivity out. We said the diffusivity didn't change much with concentration, but now it does. So we have a first term that looks like the Fick's second law that we had before, but we also have this other term that has to be there to account for the change in diffusivity with change in position. And this is just essentially a chain rule. So first we have to do the multiplication rule for differentiation, and then we need then we have the chain rule in there to get this in the final form. But this means that our change in concentration with time is a nonlinear second order differential equation. And this is really, there are no analytical solutions to this, right? This can only be solved numerically, right? So that's sort of another way. It also means that because of this complication, it's really hard to measure these diffusivities experimentally. right? So these are all sort of complications, right? The other complication that we have to consider is that before we talked about the movement of A through the lattice. Now, because we're in a situation where we have differential movement, we have different number of vacancies going from one side to the other. That means that that our lattice actually moves and our interface moves. So we have to account for not just A moving through the lattice and B moving through the lattice. We also have to think about what happens when our lattice moves through our sample. Right? So these are all things that we're going to talk about in detail today. Right? Okay, so let's set up our analysis properly, right? So first off, we're going to make the simplifying assumption that for this initial part of our conversation, that the diffusivity of A and the diffusivity in B are approximately independent of concentration for some small region, right? We're not saying independent of concentration over the whole 0 to 100, pure A to pure B, but in some small region of concentration, about 50%, we're going to assume that it's approximately uniform, right? This means we're going to be able to make the analysis at least tractable in that region. And what I mentioned before is that these diffusivities are defined so that Fick's first law applies relative to an individual lattice plane, right? This is important because as I mentioned before, and we're going to talk about in details, the lattice planes actually move. So we need to, we say relative to a lattice plane and not relative to a spot on the sample. Okay. I know that seems an odd distinction to make, but it's an important one, and we'll get to why. Right? But basically, we just have Fick's first law here that is relative to some plane, right? This looks like what we saw before. Oh, this should be dB. Shoot. I always find typos. I look at these 1,000 times. So fix this right now. Make a note. Okay, so assume that we're going to also assume that the number of atoms per unit volume remains constant, right? So that allows us to write that the concentration gradient of A has to equal the negative of the concentration gradient in B. Right? Right? So basically, if we think about that, the mole fraction of X plus the mole fraction of A plus the mole fraction of B has to equal 1, right? If we have our gradient in mole fraction, because of that constraint, they have to be related to each other. Okay. So let's consider the movement of atoms and the movement of vacancies, right? If I have this atom hopping this way, we can also think of it as the same as this vacancy hopping to the right. So an atom hop to the left is the same as a vacancy hop to the right. Right? This was a point I made before, but it's really worth reiterating. Because here we need to be concerned with the net movement of atoms and the net movement of vacancies. Right? And so we have a flux of vacancies due to the migration of A, right? And that flux of vacancies is going to be equal to the negative of the flux of A atoms. The same thing, we have a flux of vacancies due to the migration of B that's equal to the negative of the flux of B, right? There's a net flux of vacancies that's equal to the sum of these two contributions. right? And if we have that the flux of A is greater than the flux of B, right, we end up with this rule of essentially fix first rule for the vacancy flux, right? So this leads to a variation of our flux of vacancies across the diffusion couple, right? So conceptually, this might seem a little crazy, right? But if we look here, if we have our interface plane, right? And I have the net migration of A going this way, and the net migration of B going this way, and they don't balance, right? I also have to have vacancies going this way because my A is going faster. And since my number of lattice sites don't change, my flux of B plus my flux of vacancy has to equal the negative flux of A, right? So if we look at this interface, right, we get a asymmetric concentration profile that develops, right? And it's not what we saw before. It's not that nice sigmoidal shape that you get from the error function solution to fix laws, right? Right. So this is the composition of that develops across our diffusion couple, right? So if we look at the flux of atoms, the net instantaneous flux as a function of position, we have something that looks like this. And what's important here is that if I'm moving A from left to right, and I'm moving vacancies from right to left, right? Remember, we have a thermodynamic equilibrium for vacancies. That means if I have a equilibrium vacancy concentration, I have to destroy vacancies over here, and I have to create them over here. So how on earth do I create vacancies or destroy them? What mechanisms do I have for that? Right? We said before that grain boundaries are good sources and sinks, right? But a lot of places might not be near a grain boundary, right? So that doesn't help everywhere, right? So from structures, right? Have you guys talked about generation of point defects? Anybody? Well, so cold working is going to generate dislocations, right? Not necessarily vacancies, right? Okay, so.
No, I don't think so.
Okay, so I'm glad I put this in here then, right? So in order to maintain our vacancies, right, we need to create or destroy, right? So the rate at which vacancies are created or destroyed is essentially going to be given by this this balance here. But the important bit on this slide is we have grain boundaries and free surfaces, but also the climb of edge dislocations, right? Is that if I talk about climb of edge dislocations, is that a new topic to you guys?
Not new, but we haven't discussed it in a while. I don't think
Okay.
Dislocation was back with Akbar, I think.
Okay. Well, I'm glad that he covered it, but it's a really sort of pretty simple idea, right? So if this is an edge dislocation, right, and I put shear on it, if I put a shear stress on it, right, this edge dislocation can either move to the left or the right, depending on the shear direction, right? Right? So, but the only way for the dislocation to move in this direction, to go from, let me take a step back and define terms a little more carefully. So what's our slip plane here, right? So this is our slip plane. Oops. Right, where I'm moving my mouse, right? And so this dislocation glides in this slip plane, right? And what's our Burger's vector here, right? So in this case, we're going to have a net, if I make my Burger's circuit, right? And I go 1 over, 2 up, 1 over. I need to go, oops. Let me start here and make my Burger circuit, right? So I end up with a net closure failure in this direction, right? So my Burger's vector is going this way. And we remember that edge dislocations move in their slip plane in a direction parallel with the Burger's vector, right? In a direction that's orthogonal to the dislocation line length, right? So this dislocation is a line coming in and out of the plane, this extra half, which is the termination of this extra half plane of atoms, right? So this dislocation, like all dislocations, is confined to glide in its slip plane, right? The only way it can change planes is by climb, right? Remember, screw dislocations can cross slip because of their geometry, which isn't relevant to the discussion here, but edge dislocations, the only way they can change out of their plane is by climb, right? So how does climb occur? Essentially, we can have, if this is a vacancy, this atom can hop here, this vacancy can hop here, and then we have another hop. This atom can hop, and the vacancy moves here. And now this plane has shrunk by 1 atom, and my dislocation line is now in this, becomes my slip plane rather than this, right? So by climb, I've eliminated this vacancy, and I've moved my dislocation line up 1 slip plane. I can also have this atom hop here, and now I've created a vacancy, and I've moved my edge dislocation down 1 slip plane, right? So how many dislocations do I have available, even in a well-annealed crystal, right? Because this is diffusion's happening at high temperature, right? So we're going to have a fairly well-annealed structure, right? We won't have a lot of stored cold work. So what's my dislocation density going to be about?
Are you talking about like per crystal?
The dislocation density is usually given in line length per unit volume. So it has units of per meter squared. Right, so what's a low dislocation density? Right, oh, okay, cool. You guys learned something new today. So it's about 10 to the 12th per meter squared, right? How long is that?
Very, very, very small.
Well, it's 10 to the 12th meters of length per cubic meter of volume.
Oh, never mind.
Right?
I thought it was different units, but yeah. So
that's if I have a 3 foot by 3 foot by 3 foot block of iron, approximately, right? Right, because some people are not used to thinking in meters yet. that means that the total dislocation line length is about the distance from the Earth to the sun.
I forgot how weird this was. This is something we haven't covered in a while, and
Yeah,
how much it seems to defy logic.
it seems to defy logic, right? It's a lot. There's a lot of dislocations. That's in a well-annealed metal, right? What's the dislocation density in a heavily cold-worked sample?
If it's cold work, there's going to be a lot more dislocations because that's the process of cold working. Dislocations. It causes dislocations to harden the grains.
Yeah.
Right.
So the upper limit that you can reasonably reach is about 10 to the 16th, right? About 4 orders of magnitude higher. Right? So how long is 10 to the 16th meters?
I think from the Earth to not even the sun. Is that more like the Earth to Jupiter or something, or like to?
Oh, it's a lot longer than that. It's about a light year, right? So 10 to the 12th is about the distance from the Earth to the sun. 10 to the 16th is a little bit less by a factor of 2 or maybe 3, but not a full order of magnitude. Difference from the sun to the next nearest star. Right? So we're talking the amount of dislocations in a metal is actually like astronomical type numbers. Right? So there's lots and lots of dislocations, edge dislocations where this can happen. Right? But it's just kind of always mind-boggling how many dislocations there actually are in metal, even when it's well annealed, right? The fact that you can make a TEM sample, right, which is maybe, say, 100 nanometers wide by a couple nanometers thick, right, because you need it to be electron transparent. So say 50 nanometers thick by 250 nanometers wide, right? Which is an astronomically small volume. It's tiny. And you can see large numbers of dislocations in there. Tells you how prevalent these defects actually are, right? Okay, but anyway, so this is climb, right? So this is going to be the major way of eliminating these excess vacancies, okay? So the climb is actually really, really important for material properties, right? So here we have 2 screw dislocations that are on different slip planes, right? So they're not parallel with each other, right? Remember, in a screw dislocation, the Berger's vector is along the line direction, and the slip direction is orthogonal, right? So when these 2 screw dislocations intersect each other, we're left with a jog here, right? Was dislocation jog something you guys talked about, or you'll probably get it with, you'll definitely get it in mechanical behavior. Next semester if you haven't. But anyway, when 2 dislocations intersect, right? I now have a pure screw, they intersect, and now I have this kink in here. It's a little different than what we normally call a kink, but we call it a jog. But this jog is actually an edge dislocation, right? So that means the Berger's vector here stays the same, right? So it's a little easier to look at here, right? The Berger's vector of the screw dislocation is parallel to the line, right? just because I have a jog here, it doesn't actually change my Burgers vector. Remember, a dislocation is a boundary between a region that's undergone slip and a region that hasn't slipped yet. So that means the Burgers vector has to be constant everywhere along the dislocation length, right? So here my Burgers vector is now perpendicular to my dislocation line length. So that means that this A prime segment is actually an edge dislocation, right? So which way do these dislocations want to go, right? Well, my screw dislocation wants to go this way. The screw dislocation moves this way, but my edge dislocation is stuck moving in this plane, right? My edge dislocation can only move in this plane. My screw dislocation wants to move in this plane, which means this dislocation is largely immobilized. It can't slip very easily because this edge jog essentially pins it in place. The only way I need to move my edge this way, and then I can glide my screw this way, or I need to move my edge dislocation segment by climb, right? So climb of edge dislocations is actually the rate limiting step in glide often, right? In plastic deformation, this motion of these edge dislocations becomes really important. And this is really critical to work hardening in metals, right? So this is just a tiny little sneak peek of what you'll get in the mechanical behavior class. But it's just important to realize that edge dislocation climb is actually an important topic that covers a bunch of other, right? Climb and glide are distinct processes, right? But if I have a jogged screw dislocation, right, this screw dislocation can't glide because this edge dislocation, this edge segment pins it in place, because this edge segment has to move on a different slip plane, has a different slip plane than the screw component. So that means this edge part here has to climb so that this screw part can glide, right? So if you don't 100% get this, that's fine. This is a bit of a diversion from what's important for this class. Your book, the reading makes a reference that says, talks about non-conservative motion and things like that. So I wanted to throw it out and just let you know where climb processes are important in other regards, right? It's really important in the recovery, the static recovery, and annealing of metals, right? So you'll talk about this in detail in mechanical properties, okay? But this motion of defects and climb processes essentially means that we end up with a net flux of atom planes through our sample, right? So we're going to have extra atomic planes introduced in the beta-rich side, while planes will be eaten away from dislocation climb, right? If I have climb going in this direction here, right, I'm going to be growing this out, right? So I'm growing new planes over here. Over here, I'm eliminating this plane. This plane's moving this way, right? So that means I have a net movement of my lattice to the left, right? It's not just that I have flux moving through the lattice. My actual atomic planes are moving to the left. New ones are being created over here. Ones over here are being destroyed. Right? I should be careful. I hope that this camera is mirrored the same way as the slides. So, but I think that's right. The way I'm holding my hands. Right? So we have a net motion of the lattice. We can do some geometric analysis, right? It's in the reading. It's not worthwhile spending a huge amount of time on it, but it's not too difficult to show that the velocity of the lattice planes is going to follow the same form as the motion of vacancies, right? Right? So we get this expression for the velocity of lattice planes, and this is what's known as Darkin's first equation. Okay? And this comes from the fact that the velocity at which the atomic plane moves is going to be related to the flux of vacancies crossing it, right? So the number of vacancies is going to determine how fast we grow new ones over here, how fast we dissolve away old ones over here. So that means that it's going to be proportional. The rate at which these shift over is also going to be proportional to that vacancy flux. That's the fundamental physics underlying the analysis. Right. Of course, if we're thinking about material processing, the movement of individual lattice planes deep in the sample is not really of direct interest. What is important is to be able to apply this to be able to develop our laws for interdiffusion. I want to know how fast A is going to homogenize, or my diffusion couple is going to homogenize, how fast A is going to penetrate into B. I don't actually care about how fast my lattice is moving, right? But this is just an important step in getting that contribution. Oh no. Shoot. I need to fix this. Okay. I changed fonts and I guess it got cut off. Shoot. Okay. But anyway, the logic to derive this is exactly the same as we did for Fick's second law for diffusion. The difference here is we're talking about a total flux term, right? And what do I mean by the total flux term is this total flux includes both the diffusive transport of A across the lattice planes, but also the transport of the lattice planes through this section, right? So if I have A on a lattice plane and that lattice plane moves in to this thin slice, I have A transported in here by the convection of the lattice. I also have diffusive hopping of A from one lattice plane into the next lattice plane happening here, right? So that's what we mean by the total flux. The notation in the textbook is also confusing because sometimes they use prime to mean derivative and sometimes they mean prime to just mean net. So I'm going to be very clear about how I use them. Okay. But we have two contributions, right? We have the diffusive flux, which is movement of A relative to the lattice. And then we have the movement of our lattice, which is going to be given by here, right? And I'll fix this so we can this is what's cut off, right? So this is our total flux, is our diffusive term plus our lattice velocity term, right? This is just the same thing repeated. So our total flux is given by this. If we combine this, that our velocity is given by Darkin's first equation, this is the velocity of the transport of our lattice, we get Fick's first law for the total diffusion flux, which has this form, but we can simplify this. And this is what's known as Darkin's second equation, and this is the definition of our interdiffusion coefficient, right? So what do I want you guys to know about this? Okay, so this interdiffusion term couples the movement of A, the diffusivity of A, and the diffusivity of B, right? And the mole fraction terms are crossed. So it's the mole fraction of B times the diffusivity of A plus the mole fraction of A times the diffusivity of B. So this is a form of an average, right? So this interdiffusivity is think of this as a average or an effective diffusion constant or a diffusivity that explains how A and B are going to interpenetrate each other, right? And that's really the key thing to understand, right? And it comes about in a way that accounts for both the diffusive flux of A and B, the net vacancy flux of A and B, and the convection due to moving lattice planes in our sample. So we can use this to write Fick's first law in a form that we understand. That our flux, total flux of A is equal to our interdiffusion coefficient times our concentration gradient in A. Right? The negative here, or if we use the concentration of B because the concentration gradient of A and B are trivially related, we can write it in this way. Right? And if we plug this in, we end up with our second law in the form that we talked about before, right? And that's where we'll stop, right? On Friday, we'll take a look at this, how exactly this interdiffusion, this interdiffusivity works, and look at some examples of how this can be applied, right? But these are Darkin's first and second equations, right, which are used to analyze exactly what's going on in this interdiffusion, right? And this is kind of hard to wrap your head around. You'll have to see this multiple times before you can really internalize it, and that's normal, right? So out of everything we do, I just want you to take away the key ideas is that when we have interdiffusion and the flux of A and the flux of B aren't balanced, we have a net migration of net migration that gives us an asymmetric concentration profile. We have a net flux of vacancies, and we have a net movement of the lattice. Those are the key ideas. That's what I want you to focus on. Okay. Did I post? Yeah, I will do that right there. Okay. So I will fix that immediately right now. As soon as I hit stop, as soon as I end this meeting, I will go, we'll go sort that out right now. Okay. Sorry about that. That's totally my mistake. So Wednesday, come prepared with questions, right? All right. I'll give you guys the floor. floor to ask anything that you want, any clarifying questions that you have. Okay, take care.